as we've just seen, if we express a vector function r of constant magnitude in terms of the unit vectors in the r and theta direction, the polar unit vectors, then r prime is equal to r d theta dt times u theta. We want to know what the acceleration function is and how that's related to everything else. So the acceleration function is r double prime, and that's going to be the derivative of the r prime function. And the r prime function consists of a constant r multiplied by d theta dt, which is a function of t, multiplied by u theta, which is also a function of t, because as t changes, our position u sub theta, the orientation of our r vector, and therefore of our u sub theta vector, is going to change. So when we take the derivative of this, well, r is a constant. It's going to be a factor of every term of the derivative, but we're going to have to apply the product rule on these two functions of t. And we get then r times the derivative of theta with respect to t prime times u theta plus r d theta dt times the derivative of u theta. And that's easily worked out. The derivative of theta with respect to t is just the second derivative of theta with respect to t. And the derivative of u prime with respect to t is, well, it's r d theta dt here times the derivative of u prime, which is negative d theta dt times u sub r. So that ultimately our acceleration function is r times, I'm going to write this as theta double prime u sub theta for the second derivative, and then plus r times theta prime squared times u sub r. And that's not plus, that's minus. I'm going to use the magic of small slip paper that I had ready for mistake. Okay, so here's our expression for the acceleration vector. Now, if r is constant, we're modeling motion around a circle, at least if we consider t to represent time. Then our velocity vectors, well, we don't know what our function r is, we just know it has constant magnitude. It's possible that all the r prime vectors have the same magnitude, but it's also possible that they're changing in magnitude. Now, if they're changing in magnitude, and if the point moving around the circle is constantly being accelerated perpendicular to the circle, and anytime we have an arc, we have an acceleration component perpendicular to the arc, a normal component of the acceleration, then our acceleration vectors might look something like this. Speeding up in this direction, so there's a component in this direction, also curving in such a way that we have an acceleration component perpendicular to the curve, which would be toward the center. If we look at a typical r prime vector and an acceleration vector equal to r double prime, r prime can be expressed in terms of a component in the radial direction. I'm sorry, r double prime, our acceleration, and this is not r double prime. This would be our vector u sub r, and we'd also have a vector u sub theta. And the point I'm trying to make here is that r double prime has a component in the direction of u sub theta. It also has a component in the direction of u sub r, and these components are easily illustrated. We simply project r double prime onto u sub r. Well, right here is our u sub r component. So this component here has magnitude r theta prime. This component has magnitude r theta double prime. This component is perpendicular to the motion. This component is parallel to the motion, to the r prime vector. And the magnitudes of those two vectors are given very simply by this second derivative. Now we'll go on with this interpretation in a minute.